Hey guys, welcome to my new tutorial. Since I got many requests about doing a tutorial on shader coding, I thought this might be a great time to start exploring this super fun, cool, interesting topic together. As you may or may not know, I'm using shaders quite a lot for creating my visual effects, probably around 90% of the time, because I think they're very powerful. You can do a lot of different cool stuff with it. They're also very flexible and really fast because they run directly on your GPU. So it's really great for doing real-time stuff. And of course, they have a great support for many different VJ softwares like Synesthesia or Touch Designer or a Mad Mapper. So if you want to create live visual effects for these kind of softwares, it's really good to learn about them. I'm also aware that for many people it sounds quite intimidating. I get this a lot of people telling me, yeah, it's so cool, I want to learn shaders, but I don't know where to start, and it looks so cryptic and everything. And I agree that it might look like that, but the aim of this video is also to show you that it's actually not that hard to start getting into it and learning about it, and that you don't have to understand everything in perfect detail, that there's a lot of resources out there which you can use and learn from, and that it can also be very playful to just try out things and create your own effects quite easily without having to know about all the deeper mathematical aspects and so on. And also, I think it's a great way to learning all these things in a more direct, visual, intuitive way. So I can highly recommend, if you're interested into this, to start playing around. And yeah, I invite you to join me on this journey. For this tutorial, I thought I'm gonna recreate a visual effect I did these past days, which I also posted on my social medias. It's this quite cool, funky, psychedelic looking oriental carpet. I created this as part of a generative art challenge, which is ongoing. I don't know if you heard about it, called January. I think it's happening every year in January. The idea is to create a visual art piece every day for some given prompts. If you're interested into this, there's this website, january.art, January with a G for generative art. So for every day you get some interesting prompts, and then you're supposed to do something with it. And yeah, you can use code, or you can use different tools like Touch Designer or whatever. Also, please like and subscribe and tickle the algorithm in any possible way. This is always very helpful to me, so I can continue doing videos like this in the future. But back to the tutorial. So the idea is to create this whole visual, this flying carpet from scratch. Probably not going to look exactly like this, but we try to get close to it. And I'm trying to explain every step on the way, and also giving you some background information, what's behind it. Trying this to the best of how I can do it. If you don't understand anything in detail, you can always go back, check it out. I'm also going to post the code in the end, so you can check out the code and try it out yourself. Or if you recode it yourself, you can look it up and see how things worked out. Of course, it might be that I'm sometimes a little bit fast and on some topics or some things I'm doing. because it's in the nature of things that I'm sometimes doing things which are quite clear for me but might not be clear to you at all. So pardon with me, I'm really trying to to explain as much as possible. If you don't understand something straight away, you're welcome to research it, to ask me in the comments below or whatever. Also, I welcome you to like and subscribe the video if you like what I'm doing here. This is always good to motivate me doing more stuff and getting more views and more people interested into it. So yeah, please do that. And let's start. I'm going to create a complete new Shadertoy. By the way, I'm using Shadertoy. Shadertoy, if you don't know it, it's a free software on the web, on the internet you can use. It's on shadertoy.com. So it's a website which is basically so you can use it to create shaders and have them display in real time, but it also is a great platform to share your work with other people and also look at other people's work. So it's really like the Facebook for shaders, and it's a great community. I've been part of the community since quite a few years, and you can learn so much from other people, and people are really nice and kind and give you tips, and it's the perfect place to start learning about it. And it's really easy and fun to use. I'm gonna create a new shader, and then I'm gonna explain some of the first steps to get started and a bit about the Shadertoy interface, and then we go do some fun stuff. So when you create a new shader, it's always going to look like this. You got some basic setup, some basic code, which is generating this gradient. And the layout is that you have the code showing here. There are some help functions, which is showing you what is allowed, explaining a little bit about the syntax of the code of the language. The language is called GLSL. It's OpenGL shading language is the most common used shader language, I would say. So you got some function reference of the inbuilt GLSL functions. But you definitely have keyboard shortcuts like Command Enter, for example, to recompile, which is quite useful. Then on the left side, you have the output. There's also a start and stop for the time. You can use time for doing the animations. You also have a record button to record videos. And this part here, these controls, they are not part of Shadertoy standalone. So if you open it, it might be that you're probably not going to see them. And those are added controls by a plugin called Shadertoy Unofficial. You can download it for Chrome and I think for other browsers as well. So go check it out. It's giving you some extra control like this timeline, which I think is nice if you do some really timed animations. This is more like an IDE experience. You also have this mouse uniforms, which I don't use that often. There's also a function to export images in higher quality, like single frames. I don't know why it's not showing at the moment. Yeah, usually it's showing up here, but sometimes it's not showing. But we're not going to use any of those anyway. Then on the bottom you have some channels which you can use for external textures. There's also some stuff built in and music and also other inputs like camera or microphone or keyboard or whatever. I'm not going to use them as well, but yeah, they're also quite straightforward to use if you want to check it out. The basic anatomy of a shader is this. You have this main function, which is getting one input and putting one output, and it's very simple. The input is just one coordinate of the current pixel processed. That's why these type of shaders are called fragment shaders, because they're computing a color for a fragment, which is basically a pixel. And you get the coordinate, a frag coord in this case is the input variable. It is a vec2, which means it's a vector with 2 dimensions. It's got the x and the y component. And you output a color value, which is a vec4, which means it's RGBA, it's red, green, blue, and an alpha channel for transparency, though you're probably not going to use the alpha channel in most of the times, so you can always set it to 1 and will be fine. Yeah, that's it. So shaders are in that case very simple. You don't have any external libraries which are complex. You just have a very basic function set, which is good enough to do a lot of different effects, and you can also create your own functions. And you can also use functions of other people, which you can find on Shadertoy or on different websites writing about it. I will link some resources in the video, which I think are good to know, but we will get into this maybe a little bit later. I don't want to bore you too much with the introduction. So yeah, let's start. First of all, I'm gonna clean up a little bit this code and then start creating some functions which draw some basic objects, and then we can slowly progress from there. So the first function is normalizing the coordinates which you usually get in pixel coordinates. So usually if the resolution is 180 by 720, 1280 by 720, the x component is going from 0 to 1280 and the y component is going from 0 to 720. But what you normally want to have is a range between 0 and 1. So that's what it's doing here. It's dividing by the resolution. So you get a resolution from 0 to 1. But what is even better and what we are going to use for most of the time is to not start at 0 here, but we want to have the 0 in the center. So we want to have, if you imagine a coordinate system, like for graph drawing, we want to have the 0 point in the center, so everything to the left is negative, everything to the right is positive, and the same for the y component. Up is positive and down is negative. This has many advantages, especially if you want to draw objects. Usually they will be drawn by default in the center, which is good. And also if you want to do stuff like symmetry, which we use a lot, it's also beneficial to have the 0 point in the center, because then you can use some easy mathematical tricks to create the symmetry. So with maybe few exceptions, you actually always want to do that. So I'm going to change the code slightly so we have the pixel, the center, the origin in the center, and also have it normalized to 0 and 1. So the code I'm using for this is a quite standard way to do it in Shadertoy language. I'm not gonna explain the whole details of it, but basically it's it's first dividing by 0.5 and then also subtracting 0.5, so actually moving it up in the center. And then it's also normalizing, so you don't have the aspect ratio screw, so to say. So we're going to divide the whole thing by the y component. So that's it. You can just use and copy and paste this function. And the UV coordinate is usually a very common convention about having the pixel coordinate in the screen space, and usually they are supposed to have the origin in the center. So this is just a convention of naming. By the way, I try to explain most of the conventions I'm using. Some of them are quite standard for the community. Some of them are more of my own. I try to be explicit when I use them, though I might not be at times. So the next one is the output. We are computing a color here, but now we're computing this color gradient, and for now I want to change it to just output black. So I'm gonna initialize it to a vec3 0. Vec3 is normally used for colors, for RGB colors, and then if you compute the final output, you also add the alpha component, which you can just set to 1. You don't have to take care about this because it's not used most of the time. So now we are set. We have a black screen, so we have like a blank canvas. We can start to draw some stuff, and since in shaders we don't have any external drawing functions or like that, we have to create them ourselves, which is not so hard to do, as I will show you in a minute. And if you want to do more complex stuff later on, of course you can also create your own functions and collect them and reuse them, so you don't have to write everything from scratch again. There's also a possibility to use a comment tab here, where you can paste some kind of library functions which you reuse many times, so they'll not clutter your main code. But yeah, I'm not going to use this at the moment. So the first function we want to create is a circle, like very basic. And the way we are drawing stuff in shaders is mostly using so-called distance functions. Sounds like cryptic, but it's not. A distance function is just a function that is returning the distance to the surface of some of the objects we are wanting to draw. For example, for a circle, we want to measure the distance to a circle, and then we can draw the circle based on the distance. And computing a distance is usually quite easy and quite fast to do. That's why we use it, especially because the input we are having are pixel coordinates. So yeah, that's the common way to do it. And to draw a distance to a circle, you want to imagine you're getting all points one by one, and for each point you want to know what is the distance to the center of the circle. So to do that, we want to create the length of the vector towards the center of the circle. And since we have our center always in the middle, we can just compute the length of the vector. So it's very basic Pythagoras. If you want to check out the math behind it, check out length, distance to a circle, or Pythagoras theorem. It's very straightforward, but we have a function to do that, so don't have to compute all the steps ourselves. So first I'm going to create a function. It's going to return a floating point, which means just one single value between 0 and 1 or something like that. Because we are not interested in colors at the moment, we just want to have black and white values, and it's getting another input, which is the current coordinate. We use P for pointer. It's also quite common convention. And to return the distance to the circle, we can use length, which is doing the length of the vector. And of course, we also need the radius here. So you want to have a circle with a specific radius, and we are going to subtract the radius also. And what allows us to do is to have a signed distance function, which means that you compute the distance not to the center, but to the surface, like really the surface of the circle. And the distance outside the surface is going from starting at the surface at 0 and then going outwards positively, and it's going inwards negatively. So you have inwards you have a negative number, and outwards you have a positive number. That's why they're called signed distance functions, because they have a negative and a positive component. And that's quite useful for doing some stuff, which I will show you in a second why this is useful. So yeah, this is our circle function, and we can also show it. So to use it, we just gonna add it to our current color value, which is initialized with 0, and you can plus add, which is just adding something to this value. So it would be the same as to write color plus something. It's just a shorter way of doing this. So I will add our circle functions with our current UV coordinates and radius of 0.3. As I told you, the coordinate system is going from 0 to 0.5 in each direction, so 0.3 is something that is fitting in the screen quite well. And see what this looks like. Of course, I have to return something here, so that's why I got an error. Return. Okay, now you see something that actually looks like a circle. And it might be not the circle as we finally want, but is more like a gradient, and that's because it's a distance function. So on the outside you have a positive value, it's going lighter the further you get, and in the inside you have a dark as a negative value basically, and you can't see it because all negative values are displayed as black as well, so you won't see any difference here. And now the next step, what we want to do is to not create this soft gradient, but have first of all like a solid circle with a solid border. We still usually want to have a little bit of softness on the border, not like 100% black to white, because then we would get problems with aliasing, which doesn't look good. So we want to have a very little smooth border. And what we usually use to do that is a function called smooth step that allows you to interpolate between two values, for example 0 and 1. But in this case we want to interpolate between 0, which is probably somewhere here, and just a very, very small value outwards, so that you get a small smoothness also. So one way to do it would be just cut off straight. So if I would do something like this, if the color, if let's say, let's put this here, D, I always use D for distance as a convention. So if I say D is less than 0, then we want to have the circle white, so we add 1. Then you get a very sharp edge, which you can see gives this blocky aliasing artifacts. So we want to do it better, and the way to do it better is to use the smooth step, which is interpolating between two functions. A smooth step is just, imagine like a fade function in your video software or audio software. If you use something like that, you want to have a fade of the sound fading in, but you don't want to have it like a straight line. You also don't want to have a linear line which has some discontinuities, but you want like a very soft fade in. So to show you how this looks like, I'm using Graphtoy here. Graphtoy is another software by the creators of Shadertoy, also specifically Inigo Gilles, who is the shader god, so to say. He's the creator or the founder of most of these softwares, and he's also one of the guys most knowledgeable on all these kind of computer graphic tricks. And I can highly recommend check out his website, which is, I think, one of the best compendium of computer graphics and shader coding, and very, very well explained, and probably most people around today using Shadertoy learned from him or based his knowledge on his resources. I specifically learned most of it from him because it's very, very, very rich. Since, I don't know, 15-20 years he's been posting stuff regularly on his website, and it's very well explained, all the also very complex math behind it, and it's really cool. So definitely check it out. I'm gonna link it also in the description. But back to this Graphtoy. It's basically a tool to visualize graphs, and it also has many of the functions which are used in the shader, so you can visualize how a function might look like, and that's very, very handy most of the time. So to show you how a smooth step looks like, you take two values, let's say 0 and 1, and you have our x coordinate, and it's just doing this. It's not a straight line, but it's got this smooth fade, so it's smoothly interpolating between the two values. And you can plug in different values, and it will do the interpolation between those. So that's how it looks like. And now we want to interpolate our distance functions to have a soft edge. So to do that, I'm gonna use smooth step. We start at 0, which is the edge, and we want just to have a little bit outside. So we're gonna use 0 and something like 0.21 even. If I can use a bigger value, I can show you what this looks like. And then our distance. So now we have a very soft edge, but we want to have it even tighter, so we can use something like this. You see it's still a little bit blurry, but it is still looking much better than the blocky one we used to have before. You can have it even smaller, like you like. This is usually resolution dependent, so you wanna kind of make this dependent on the resolution either, or there's also some some other specific tricks to make this work automatically. But yeah, I'm not going to go into this right now. I'm just going to use a fixed value, and that's fine for now. So far to the circle, and the next thing we want to do is to have not only a solid circle, but just like a circle outline, so just like the rim of a circle, so to say. And now we can make use of the signed distance function, because we know that here is 0, and we go negative here, and we go positive here. And if we do an absolute function called ABS usually, we can make everything which is 0 positive, and this is basically just reflecting something on the other side. And we use this a lot for doing mirroring stuff, or doing basic symmetry. So I can show you how this looks like, just to get an idea. If you just type x, you will just have this straight line, and we use abs from x. We say we're gonna reflect everything which is negative on the positive side. So everything which is here is gonna be reflected upwards. And that's the principle we are using here. So we usually do the abs, and then we want to subtract a small value because we want to have the edge a little bit bigger, and that the rim a little bit bigger. So we use something like 0.1 maybe. That's maybe a little bit too big, but you can see where it's going. So maybe something like this. And now you have a rim, and you can do this basically as many times as you like to get multiple ones. And we call this onion technique because you can get this this concentric effect. And basically you can do this with any kind of distance function. So now you get like multiple ones, and this is pretty cool. So, but for now we're just going to do one, and we are done for the circle for now. Except one thing we want to change now is black, so that the foreground is black, which is 0, and the background is white, which is 1. We want to invert that, and so the circle is white and the background is black. So we're gonna subtract everything from 1, and this is basically inverting everything. So great, now we have a white circle on a black background, which is already something, therefore, that we started with nothing. But we're not gonna stop there, obviously. We wanna continue doing more stuff. So what we're gonna do next is to introduce some colors. Also, black and white stuff is cool. The idea of this, the challenge I did originally was not only the couple, because I actually combined two days together, and the other prompt that was, the first prompt was to design a rug, and the other prompt was to use a generative color palette. And I do this a lot. It's very easy to do, especially for some basic rainbow colors. You can easily do that, and it's easy to use, and you can get some cool color gradients, like the color gradient you saw in the beginning. If you want to have more specific color designs, then of course you can also use your own colors which are not generated, and that's also what I'm doing sometime. But now we create the rainbow function color palette, and to do that I'm gonna create a new function which is going to return a vec3, call palette, and it's as an input it gets just one floating point value x, which is giving the position on the gradient. So we want to have a smooth gradient, and the position x is just like giving us the position on the gradient. And we can also visualize it quickly to see how it looks like. I'm just gonna override the current color value with my palette function, and we're gonna use the X component of our screen space. And of course we get an error because we haven't anything defined yet. So to do that, we have to define something. And what we usually do to create a generative color palette is to use a sine or cosine function for each of the color channels RGB, and then offset them slightly like this. So we get some overlapping wave functions, and this will then create smooth gradients with some rainbow colors depending on the offset. So I will show you in a minute how this looks like with actual colors. And by the way, I don't know if I mentioned it in the beginning, you don't have to understand all the complex or maybe complex looking math behind it in detail. You just have to know the functions, and you have to know how to use the functions, and the rest is just about you playing around and get an intuitive understanding of what the functions are doing. So you don't have to understand the math, and you don't have to be intimidated by the math that you may not understand. If you do, it's great, and if you don't, you will probably get a much better understanding of it if you just play around with it, because then you actually see what it does and actually get some build some relationship, so to say, to the functions and what they are doing and how you can use them. So yeah, I invite you to, if you're intimidated by math in general, switch off that part that says I don't get this, this looks bad, I don't want to know about it, but just play around with it and just don't think about what it actually does or what it's supposed to do in mathematical sense, but just see how it looks visually. And if you're interested in math, of course, go for it and explore and get your use your knowledge to build cool functions. So I told you I'm going to use a cosine of x, and of course we want to have a vec3, so I'm going to initialize a vec3 and multiply it by x, and of course return that. And for now we just get a very soft gradient from white to black. One thing we also have to do is to normalize it, because a cosine function by default is returning a value between -1 and 1, but color values always have to be from 0 to 1. So we want to first multiply it by 0.5 to kind of compress it, make it like go from 1 to, or from -1 to +1 to -0.5 to +0.5, and then we shift it by 0.5. So we will have the range from 0 to 1. And if you don't get this, I can also show you visually. If you do a sine or like cosine, let's do a cosine. So you see it's by default going from -1 to +1. And if we multiply it by 0.5, we're gonna have it from 0.05 to 0.5, and then we shift it up 0.5, and then we get, that's the function we want, and we will probably use this quite a lot, because in many places you want values from 0 to 1, not from -1 to 1. So yeah, that's a very handy trick to remember. Yeah. And by the way, I'm almost all the time using the syntax where I cut off the 0 in front, but this would be like writing 0.5 is the same like 0.5. It's just a kind of common lazy convention in shaders. It might be looking weird to the untrained eye, so I just want to point out that that's how I'm doing it most of the time. I don't know why, it's probably just laziness, or just writing the least amount of code possible to get as much stuff in one line, which sometimes is handy if you create complex expressions. But yeah, this is basically the same thing, and you can also do the other way around. So if you want to say 0.0 is also a 0 with as a floating point. In WebGLSL, you always have to declare floating point with a point. You cannot just do 0. This would give you a compiler error, because then it will be interpreted as an integer. It doesn't do any implicit casting. And other environments this might work, but here on Shadertoy it doesn't. So yeah, always use a point somewhere, either before or after, and, either on the left or on the right side, or both, or like in the center. So so the next thing we want to do is to normalize also the input. So we have normalized the output. We also have to normalize the input to the 0-1 range, and the input expected for a cosine and sine functions is usually going from 0 to 2 pi, where 0 is the beginning and 2 pi is the end of the whole period, going up and down. So we want to multiply by 2 pi to get it into that kind of range, and we do 2 times pi. Of course, pi is not defined by default. We have to define it ourselves. 3.14592, this should be enough. And of course, pi. By the way, define is a so-called preprocessor macro, so-called macro. It's basically defining expressions which are then later searched and replaced in the code. So every time I use the symbol pi in my code, it will be replaced by this number, and this is a handy way to introduce constants without having to define variables, because in the main level you cannot define variables. You would have to make global variables which can only define in the main functions and so on, and this is a bit nasty. So this is a more straightforward, better looking way to do it. So now you can see we got a gradient. It's basically a cosine function in visual terms. And the next thing is to get some color, so we have to do some phase shift, and this is also very easy. We just have to, so this is computing the sign for each channel, RGB, all of the channels of the VEC3, and we want to shift some of the channels to get some color, overlay, some overlaying gradients. So here you can basically write everything. Also the vec3 supports integer as initialization, so you don't have to use floating points, which is cool. If I use a phase shift of 1, remember we have everything put to the 0-1 range, so you can use zeros and ones here. We will get this. So you can see that this shifting the green channel to the left and the red channel to the left, so you get this cyan and red thing. Sorry, the green and the blue channel. If you just shift one channel, you will get different outputs. If you just do a very small shift, you will get something closer to black and white. But yeah, basically you can write everything here. What I'm gonna use here is a 10, I think. This looks like a good rainbow. Also, they can be indefinitely small or big, the numbers, because it's a science. Periodically they will wrap around every cycle. So in this case, in the 0-1 or in the 0 to 2 pi range. So yeah, this is basically just giving the proportions of the phase shift. And this looks like a quite cool, funky rainbow, so we're gonna go with that. And we can also use it to color our circle. So let's remove that and multiply it with the color. And because the color of the circle was everything white where the circle is, and if we now multiply it with the color, we get the color only where the circle was, and the rest is gonna stay black. So this is the intuition behind that. So uv.x, and yeah, you can also increase the period here. If you increase it by something very big, then you get this kind of a higher frequency pattern, and if you want to multiply it by something small, you get a very soft gradient. But we're gonna leave it at this, I think, maybe 2. Maybe times 2, sorry. Yeah, no, I think 1 for now is fine. So now we have a colorful circle, and the next thing we want to do is to create some more interesting base objects, which we then can arrange and multiply and do funky stuff with it, so we get more complex patterns. But we want to start with some basic shapes. The next one is going to be a square. So to do a square, I'm also going to create a function, float square. Also going to get a vec2 p and a vec2 for the dimensions. We call it s for size, and we want to have a dimension in the x and the y dimension, to have a width and the height of the square. And to do a square, we also, of course, using a distance function here. So we measure the distance to the lines of the squares, and from there we build the whole square. I'm going to show you step by step what's the intuition behind that. First, I'm gonna use place this by my square function. Square uv vec2 0.3, and if you initialize a higher dimensional vector like a vec3, which is a vector which has x and y with just one value, you will get the value for both of the components. So this is the same as writing 0.3, 0.3, which is of course handy if you want to initialize them with one value. And of course we have to define something here. So first we're going to measure the distance to a horizontal line, and to do that we just use our horizontal line, which is the x, and we want to have the distance, so we're gonna use our s value, which is saying how much lower or higher we want to go, and use the extension in the x direction of our scythe, so it's the height, so to say. And of course we have to return it, and of course I told you something wrong. This is creating the functions in the height. We wanted to have the horizontal first, and for the horizontal we have to measure the height, which is the y component. So for now I'm also going to turn off the color to not confuse it. So now you can see if we put 0 here, we're going to have it in the center, and if we move up, we're going to have it up. So the y component is measuring the height, so to say, of our final square. And now we don't have a square yet, we just have a line, and we want to have more lines. So we're going to do the same for the x, and we also combine them with the operator that is called max, which is giving us the maximum value of both of them. And what it's basically doing is to have an intersection, so it's basically intersecting the distance to this line to the distance of this line, and we get the final value. So we will get something like an what's it called, an arc or a corner. So I'm going to do this, point x minus ps point x. So now we get yeah, almost something like a square, but as you can see it's still open on the lower side. And to fix that, we're going to use the trick we used before, which is this absolute function symmetry trick, because as you remember in the beginning, our origin is in the center, so everything below here is negative. And if we use the abs function, absolute function, we're gonna push this into the positive side. So everything which is negative is mirrored or like projected onto the positive side, and the positive is already defined, which is this one. So we will basically get, yeah, we're gonna basically mirror on this axis, and yeah, this is gonna be a final square then. So we're gonna mirror, of course, on the x and on the y at the same time, and we can do this by just using p abs.p, because it's a vector, it's doing both components. That's the cool thing about this vector functions. Most of the functions in GLSL work for floating points and for vectors alike, so they have the same name, which is cool. And of course this was the wrong function. We have to do this in our square, and now we have a square. And if you change the x component here, for example, we will get a more wider square. And yeah, but we're gonna stick to a it's not basically a square, it's actually a rectangle, so maybe we call it rect for rectangle, because a square has always has the same extension in x and y. So this is so much to the setup, and now we want to create a function that is drawing us some interesting pattern, which we can then use for our rug. So we're gonna create a function to a pattern, float pattern, and now this is still in distance function space or convention, so to say, and we're gonna collapse the distance function then with using our smooth step and the main function. So this will have some, I'm doing this, I will show you later, but it has some advantages because then we can reuse the distance functions to also introduce some color effects. So that's why I made the design decision to separate the collapse of the distance function, so to say, from the distance function itself, from the pattern function itself. But you will see later why this is useful. So this is also creating a rec 3, rec 2, and nothing else. And I will introduce initialize floating point value d. If you work with distance functions and want to initialize variables, always initialize them to something very big. So we can use one with very many zeros, or we can use the more scientific syntax, 1e9, which is 10 to the exponent of 9. So it's basically a 1 with 9 zeros, and that should be sufficiently big. I think you can also even write something like infinity. I don't know if that works. I don't know. I think some of the GLSL implementations have infinity implemented. I don't remember what's the right syntax for that. But yeah, I'm going to use 1e9, and return it also, and then we're going to use it here. Pattern, and of course it doesn't get another input, and I'm going to copy this here, and we're gonna probably we have to rename UV. We don't have defined, it's P in here. So okay, this is not changing anything, but it's just to organize the code a little bit so we can create our functions separately. And we also want to add a circle. So what I'm going to do now is to create some basic shapes, overlaying them together, and then we're going to use some different functions to create more complex shapes out of the basic ones. So we have the square and also the circle, and because we might want to change the coordinates at times, we're gonna create a backup vector for our initial coordinates. Always use BP as base pointer for our initial P pointer prior to any transformation, so we can always reset to the original state. So think of this like kind of a state machine code where you do some operations and then reset it and then do some other operations. So it's very, very basic coding structure. And yeah, first we're going to draw a circle as well, and what we want to do is to use the onion for each of the elements. Onion is creating this outline thingy. Circle. Sorry, 3. the vector a little bit smaller. And now we want to combine them. So I say here, I rename the variables now float C for circle, C, and float S for square. Sorry. And then we want to combine them both to final D, and to combine distance functions so that you have both components basically as a union added together. You use the min function, dmin, because you want to get the minimum distance to both. So whatever is closer is gonna be our final value, and this is the distance function arithmetic, or the distance function operator for plus, so to say, or for a union. S and C, and now we have them both combined. And now what we want to do is to have two circles a little bit apart from each other. There are multiple ways to do it, but now I'm going to just copy and paste the code and offset one to the right and one to the left. We don't have to initialize S again, but we have to reset our vector to the initial one, and for this one we want to set offset X to the minus 0.2, and the second one to minus plus 0.2, and of course you want to use a new variable for S2 here for our second. Sorry, this was supposed to go for the circle, so I'm gonna redo this. Sorry, I want to do this for the circle, not for the square. So C2 and P. So here P is basically resetting our initial state. And now we want to offset this one to the right, to the left, minus 0.2, and the other one to the right, plus 0.2. And then we want to combine both. So we want to add the second one to the first one. To do this we can use the min function again. Min C2. And now we have got two circles. And this looks already quite cool. And one other thing I did in the original version was also to do the same for the squares, but I'm not gonna copy and paste the code, but I'm gonna use a little trick which we can do if we have the shapes sufficiently apart. Is to use the symmetry trick also again. So if you use symmetry and then subtract some value, use the abs function, subtract some value, you're basically copying or like mirroring the shape to the other side of the screen. And in this case, if they are very close together and you want to have them overlapping, it's not going to work because the mirroring is just it's just gonna do a union of the whole final shape, so you will not get these parts here. We couldn't have done this with the circle because you want to have them overlapping. Just to see how it would have looked otherwise, if we want to reset it here, draw another circle. if we wanted to do an abs, oops, you can see this is kind of mirroring the circle, but you don't get this overlapping shapes which we want. So in this case we created 2 instances of the circle. But then usually you don't want to create many instances of the same thing, but rather use like mathematical tricks to mirror and duplicate stuff, because it's more efficient. In 2D world it doesn't matter so much, because we just have to do it once, but if you're in 3D world, you can also use distance functions in 3D to create 3-dimensional objects. And there it's very crucial to have as few complex operations as possible. And a circle, like a length operation, is quite expensive because it has some square roots in it, and you want to have as few as possible of them to get the code very fast running, because for 3D you have a lot of iterations for the same shape. But yeah, we are here in 2D world, so we can easily copy a few instances without problem. So much to that. I'm going to remove this again, and also this to go where we used before. But if they are, for the squares, we want to have them more apart, so we can use the trick. So I do x minus 0.2 maybe. Maybe even more, maybe something like this. And also what we want to do is want to rotate them, have them slanted like in a 45-degree angle. And to do rotation, the most easiest way and the most, I would say, elegant way to do is to create a rotation matrix for a 2D rotation, and then multiply the vector with the rotation matrix. And this sounds complex, but it's actually not so hard. And also this is one part where you don't actually have to understand the math, you just have to know how to define it and how to use the functions. But if you do want to understand the math, go check it out. Ask ChatGPT or look it up on Wikipedia or Google. And I'm gonna call the function rod for rotation. It's gonna get an A for an angle, and it's gonna return a mat2, which is a matrix with 2 rows and 2 columns. And a rotation matrix is defined by some sine and cosine operators, functions. So in the first line we're gonna have a cosine of the angle, and then a minus sign. And on the second row we're gonna have a sine and another cosine. So this is, of course we have to return it. It's gonna do rotation, I think, in clock direction. If the minus would be here, it would be in the other way around. But yeah, this is just a very handy thing to remember. You'll probably use it many times if you create shaders. I always have this in my library setup. So yeah, now we're gonna use that, and the cool thing is we just create the matrix, so we don't have to we don't do the rotation yet, so we can do the rotation in place, which is from a code-wise standpoint quite more elegant to do. So we don't put the vector and rotate it, but we just create the matrix, and then we can just multiply the vector with the matrix and it will rotate the vector. So we do this for our output vector, and I think we first apply the rotation, then the translation. I never know which is the right order, but we will see. X. No, we don't actually have to do that. And the input to our rotation function, because it's sine cosine, it will always be in radians, so from 0 to 2 pi, where 0 is 0 degrees and 2 pi is 360 degrees, like one full turn. So 1 pi would be 180 degrees, a half pi would be 90 degrees, and a quarter pi would be 45 degrees, and that's what we want. So 2.25, which is a quarter, times pi. And of course, no, I was wrong. We have to first do the translation and then the rotation. And there we go. And I'm also gonna make this a little bit smaller. Maybe just 0.3. Something like that. Yeah, let's leave it here. Cool. Now we have some basic shapes. We can also activate our color again to make it look a little bit more funky. So now that we have our basic setup, the fun start can begin. We can now use some cool tricks to multiplies and fractalize and yeah, do some kind of transformations to our basically our coordinate system, so we can repeat this shape in different interesting ways to get some more complex shapes. And the first thing we are going to do is we want to arrange this whole thing in a circle, so to have some kind of mandala structure. So we can just like copy it within the circle, so you have like, yeah, just yeah, you see how it looks like. And to do that, we want to, because all the transformations we are usually doing to get this kind of complexity is on the base coordinate system. We basically change the space of the coordinate system to break it up into smaller spaces. And then we can draw in these spaces, and this is effectively copying or multiplying our initial input or our final output, so to say. And for circular stuff, we want to use the polar coordinate system, which is creating the coordinates within a circle. We want to use a function or create a function that does that. We call it 2-polar. It's getting the vector as an input and also returning a vector as an output. It's just a transformation. And a polar coordinate is also 2 coordinates, and the first one is the radius. So it's the distance from the center to the circle border, and the second one is the angle, which is going around the circle, also in a 0 to 2 pi range. So we're gonna use R the radius we compute like we did before, just use the length, just this basic Pythagoras. And the A, we use a special function called arcus tangens, or atan, and this function is basically also using Pythagoras to get the angle from a vector. So we use the y and the x component to get the angle of the vector. So if you have a y at the x here and the y here of the vector is here and here is 0, you want to have this angle. And this is what the atan is getting us, and this is a very smart atan, which is not only getting us the angle within 190-degree section, but it's getting the angle of all the sections. So you have running from all 360 degrees, so all 0 to 2 pi. So yeah, we want to, the first input is always the y and the second is always the x, and that's it. And then we want to return it, also put it back into vec2, and with the r is the first coordinate and a is the second coordinate. And we want to apply the transformation before we're gonna copy our vector, because we want to have this applied to everything we can do afterwards. So we do p to polar, and if we just call this, it will call this with the initial vector and then replace the initial vector with the vector. So it's basically transforming this vector in place. And if we do this, we will get some weird spaceship looking shape, which can also be interesting for some stuff, but yeah, might not be, it's not what we want as the final output. So we're going to do a few more things, and one of the things is yeah, the basic idea is that we want to repeat our shape along a circle. So we want to convert it to polar coordinates and then do some transformation or some repetitions, and then we have to convert it back also, so we can draw the shape in the same format, in the same dimensions as it used to be drawn in the original Cartesian coordinates. So what we want to do is to create an inverse of this function to get back to Cartesian coordinates, and we also gonna define it. It's called from polar to p, and to do that we're gonna use the sine and cosine to get the circle coordinates back. We want the circle coordinates, and then we want to multiply it by the radius to get the circle coordinates from polar. We use cosine and sine, cosine from y and sine from y, because y is our angular component, and then we want to multiply the whole thing by our radius, which is the x component. And of course we have to return it also. And now to check that everything is correct, we're gonna apply the inverse after the two polar transformation, and it should give us the initial setup, the initial coordinates again. And of course the function is wrong, polar from polar, and here we go. So now we have the same as we transformed and then transformed back, so basically didn't do anything. But now the cool thing is that we can do some stuff in between. And the first stuff we want to do is to make a repetition along the angle, along the circular thing. So you want to repeat the objects multiple times along a circle. And to do a repetition, there's multiple ways to do that. But one of a simple, straightforward way is to use a function called fract. And it's basically a very simple mathematical function which is giving you the fractional part of a floating point. So if you have 1.4, it's basically giving you the 0.4. So it's just cutting off the fractional part and returning it. And this sounds quite basic, and it is, but it has very useful properties. And this should do something. You already see the space is kind of broken up in some squares because we do end 4 times, so it's going like 45 degrees each step. But we have some discontinuities here which don't look nice. It's actually not what we want. And to fix that, we have to realign our coordinate system. It's like the thing we get out to be zero-centered again, because as you can see, if you have this one, it's not zero-centered, but we want to have the center in 0, so have a negative side on one side and a positive side on the other side. So we have to also subtract 0.5. And this is looking great. So we get something here, which looks like some basic mandala shape. And we can, of course, increase this to something like 8. And we get some cool looking shapes. And we can also use an ups function I think I used to do some mirroring. And if you use, usually you do a subtract this number, you will pull the objects apart, but if you use add a number, you will push the objects more together. And you can see how this looks like, and here you go. We get some interesting looking shapes, and if you put this to something like very high, you get something very interesting, flowery like. So yeah, this is always a cool function to draw kind of circular mandala structures, and I use it quite frequently in one way or the other. You can also use it in 3D functions. So yeah, this is a handy function to use. And let's see what this looks like. Yeah, let's go for that. And another thing we want to do is to use something called a kaleidoscopic function system. This is also a very neat trick to get more complexity out of very simple stuff. And what it is doing basically is iterating a few times and computing some simple function, which is usually doing something like a mirror, like this function here, and some rotation. And this will create some interesting looking shapes, and you can tweak the parameters as you like to get some more interesting fun stuff. And I think we want to do this before the polar. I mean, there's different ways to do it, but one way is to do it before the polar. And I will deactivate the polar coordinates for now to show you how the effect looks like. And we start with a loop. If you don't know what is a loop, this is a loop. A loop is basically repeating something multiple times. So everything in within the body of the statement is repeated as much as the loop defines. So this is very basic syntax as you have in C or in C++. It's pretty much the same in GLSL. They're very much like C-like programming languages. So the syntax is you define an initial variable, usually called I for the iterator. You have to use semicolons for the different statements, and you're gonna have a testing condition to have said, okay, we want to repeat it 4 times, and then also increase it each step. I++ is just increasing each step by 1. So this is just the syntax for saying we want to repeat this 4 times, and the value is always increasing, so it's going from 0 to 3. And then we can do some stuff. For example, do a rotation by, let's say we have a rotation and base it on pi, and what we usually do, because we are in radians, say a quarter pi, and then we want to do some mirror, but just in the x direction. Abs x minus 0.1, let's say, something like this. And this is already looking good. I don't know why there seems to be something missing here. Ah yeah, it's because we just mirror in one direction, not in both. Could also mirror in both directions to get something more symmetrical. And yeah, this also already looks like some interesting fractal. And if you change the size, you can change the size by just multiplying the initial coordinate with a bigger number to make it smaller effectively. You can also see how this looks like. And of course you can play with the symmetry, for example. Here you can get different symmetries. If this changes something. Yeah. So something like this is, for example, is really nice. Hexagonal symmetry. I like this a lot. So change. This was quite a long video already. I'm gonna leave it at that and then come back with the second part of this tutorial, where we gonna create even more complex structures and also learn how to animate them, and then finally create our whole rug, put everything together, and yeah, make it animate, make it floaty, and all that kind of stuff. So thank you for joining me on this one, and see you in the second episode.